Welcome to my talk, Lakehouses for Data Engineers, what you need to consider to build efficient ETL pipelines. I'm Nadine, and I'm part of the OneHouse team. OneHouse is building a lakehouse platform that uses Apache Hoodie under the hood for incremental processing and other tables and other services and features. I'm an Apache Hoodie contributor, and prior to OneHouse, I was at Rockset working with real-time analytics. And prior to that, I was in the at Bose working at the Bose augmented reality team. You can find me pretty active on LinkedIn at Nadine Farah. You can also find me on Twitter at nfarah86. So for the agenda today, we're going to talk about a little bit about batch processing and some of the things you need to consider. And then we're going to switch gears and we're going to talk about a new framework, which is the incremental processing framework. From there, I'll finally end on how Uber leveraged Hoodie's incremental processing framework to scale for near real-time analytics at petabyte scale. And if there's time at the end, we'll do a Q&A. So let's talk about batch processing. I'm sure most, if not all of us, has at some point built a batch processing pipeline. And you have what I call game over moments and near game over moments. A game over moment means you get a complete failure. You have to go back to the code and update it to get past that failure. A near game over moment means you're kind of dancing through a threshold where it's not a complete failure, but past that threshold, you'll get that failure. So needless to say is that a near game over moment can lead to a complete game over moment. So let's talk about what some of those moments are in this architecture. When data is ingested, it first goes through a data pipeline, some data pipeline that you built. One of the things you might encounter is an ETL failure. Now, I'm not going to go over all the different types of ETL failures you'll get, but I'll cover some of them to demonstrate my purpose. One of the first failures you can get is surrounding around data sources. For example, if you've worked with streaming data, you might have encountered schema changes where a data type was changed from one type to another, or a company just decided to add some fields and columns for the sake of it, and now your data pipeline fails. This is an example of a complete game over moment. Other moments could be, for example, with data ingestion. So if you're dealing with streaming data, at some point in time, you're going to experience tons of ingestion. And if your processing speeds are slow, you can encounter a complete game over moment. You can't ingest all the data. So you need to allocate faster CPUs and multiple cores in order to simultaneously handle these processes and threads, and also to handle the volume of data coming in and to reduce the data latency of how much it takes to ingest that data. Other types you can experience is backfilling without worrying about partial writes and rollbacks. Again, the purpose is not to go through all the ETL failures, but to demonstrate some type of game over and near game over moments you can have. The next thing you might experience is partial updates. And so partial updates have a high and inefficient resource utilization and data latency. We're going to talk about what those are. So typically when you have an incoming batch, you have to reprocess that incoming batch in order to get the new records or updates that you'll get. And so typically what will happen is you will create some sort of reference table, like a hash table, where you'll store all the records with the primary keys in that reference table or hash table or whatever you want to create. Now, when you have a new incoming batch coming in, you're going to compare the incoming batch with what's stored in this temp table or reference table through a join. The results of the joins are the updates, and then from there you'll do a complete table rewrite. And as you can see, that if you keep doing this at petabyte and exabyte scale data, well, you can reach a game over moment. It might not be obvious depending on how much data you have, but these are considerations to take in. But even let's say your workload is 10% partial updates, you still have to do a full table scan and rewrite the table in order to accommodate for those updates. And if you just narrow down to partition level, well, you still have to do those partition level updates. So you can see how the resource utilization and the compute power needed is very, very, very high. Now, the other thing with partial updates and reprocessing tables, we inevitably have to talk about merge operations. So with merges, typically when you completely reprocess the table and you're comparing records, you might perform a full merge operation in order to get the changes and do a complete rewrite. And these merge operations are also very, very, very expensive. But all this is to say is that when you build all of this and you finally, your data passes through this data pipeline, you finally create your raw table. But and so when you get the raw table and now you have your data, you might pass it through another part of a data pipeline where you might experience expensive upstarts. So this is actually a real use case that I've seen a lot of customers or people that I've worked with encountered this type of architecture. So with expensive upstarts, if you have, let's say you have data, an incoming batch of records with some primary key stored at a row. When you have a new incoming batch of records coming in, you're going to have to do the comparison to see what the updates are, and so you're going to experience these merges. The results of the merge are stored at a temp table, and at some cadence, you're going to do a complete rewrite of the derived table to accommodate those changes. And depending on how frequent you have that cadence, now you're going to experience slower and much more stale analytics. And as a result, your table could be updated within hours or days or maybe even weeks, and now you get delayed analytics. But in my opinion, this batch processing architecture for where we're at in this industry, especially with the whole new AI or AI generation or whatever you want to call it, is actually unsustainable. The amount of data we're going to have in the next 3 to 5 to 10 years is going to be at least 10x to 100x with where we're at in the trend in the industry. So this batch processing architecture has existed for 10, 20 years or so. It's nothing new. But back then, the amount of data we had to ingest and manage was so much less than what it is now. And it's my opinion that the batch processing framework will become deprecated at some point for 3 to 5 years. It's just slow, the data is stale. And if you're trying to create use and value for your users or even internally at your company, this type of architecture will eventually be deprecated and you're going to have to resort to something else in order to keep providing value. No one wants a slow AI app. No one wants a slow personalization app. It's not going to happen. I know I get frustrated after a minute. I'm like, you guys, what's going on? And so this brings up to some of the main recaps of the batch processing architecture. And now we're going to go ahead and switch gears, and we're going to talk about a new processing framework, which is the incremental processing framework. So typically in an incremental processing framework, what you'll have a whole bunch of sources that you'll ingest, and you can have upserts as well. But the primary primitive of this lakehouse architecture, or kind of this supercharge your data lake with some features or capabilities, I want to say, is one of the things you need to talk about is you need to have indexing capabilities. That is the first primitive in order for this architecture to sustain that we need to talk about. And indexing, again, I'm sure as all of us know, is to be able to locate a record really fast. The other thing that I think is really important to talk about is data mutability. In order to perform row level updates, right inside, you need to have data mutability. Much of the data lakes, in fact, all probably data lakes are append-only workloads. This is why you have to do a full table rewrite. So when you can update the row in place and make that switch, now you save on that complete table rewrite. So you don't need to rewrite petabytes or exabyte scale data. And then finally, one of the other primitive that we should talk about is, besides indexing and data mutability, is being able, to efficiently handle upserts. So in this type of architecture, when data is ingested, you'll create your raw level data. But in this case, when you have upserts, you can update the row. You can create your raw layer and not perform these expensive processes that we saw in the batch architecture. Now, if you're creating a derived table where you want to build your business level analytics, you can do an incremental pull. So what you can do is that you'll get the changes, what is happening, and you can only pull what those changes are, and then directly update the derived table without doing a full rewrite or without performing a full expensive merge operation. And so when you can completely do that, you get much faster analytics. And so this is an example of what the incremental processing architecture looks like. And at the view, you can see how simple this architecture looks like compared to the batch processing architecture. The data lake here are supercharged with capabilities that can efficiently handle the nuances of upserts and data mutability and indexing in order to build more efficient applications. So this is the take-home message for the incremental processing framework. But essentially, one of the key primitives that you want to consider is indexing, data mutability, and you want to be able to incrementally process these changes in order to update the table without doing full expensive merges and rewrites. And now this brings me to talk about how Uber efficiently scaled for near real-time analytics in Apache Hoodie. So back in 2016, Uber was already experiencing petabyte scale data, and they were using an immutable store with HDFS, okay? And so, as you can see, in 2016, Uber was, already experiencing these pain points where they were getting near game over moments. Those near game over moments at petabyte scale turn into a complete game over moment, and this was how Apache Hoodie was created. Apache Hoodie is basically a data lake platform that supercharges your data lakes with indexing capabilities, data mutability, and incremental updates, and table services for data, for clustering data, cleaning data, and so many more features. So in Uber's architecture, when they were writing and creating their raw data sets, they had upserts and all these things, and they can just completely update the raw data set. Now, if they wanted to build their model tables, they will do an incremental pull to just pull those changes into the derived table, and they can do the joins or whatever, but all the updates were completely just doing row level updates on their model table, and you can join from either any of the raw data sets, or you can join from outside data sources like NoSQL and SQL databases. And this is one of the main reasons that they're able to scale their applications now. Now, back in 2016, Uber had petabyte scale data. Now I'm sure that's a lot more. I don't know what that number looks like, but under the hood, they're using Apache Hoodie to power their rideshare platform. And so this brings me to recap on Apache's Hoodie incremental processing and how they built support tools for change streams and from diverse sources in incremental processing, and being able to efficiently join from diverse data sources in order to create business level analytics that is used to power. So one of the cool things that Uber did is, let's say you have late arriving data or bursty writes, right? With the incremental processing framework, you can let's say you tipped a next day level, you can update your derived tables with those tips amount. Let's say you want to update the driver's total amount to include the tip. You can efficiently do that with this type of architecture without rewriting petabytes and exabytes scale data. And I have some resources here, which is with Google's blog architecture. I think this is a really great blog that talks about how they scaled for their application. I'm part of the Apache Hoodie community. Apache Hoodie community has about 3,000 plus members in Slack, tons of activities on GitHub. And so if you would like to join and learn more and build with the community, you can scan the QR code to join the Hoodie Slack. I'm very active on Slack and working with different people. So, and if you like and use Apache Hoodie, please give us a GitHub star. And I'll go ahead and be happy to do a Q&A now.